So to this point, we've focused on reactions that proceed primarily from reactants to products, and the product dominate after the chemical reaction has taken place. And a good example of this involves combustion of gasoline, and of course the heat, the release of enthalpy in that reaction, drives it forward. So when we're reacting carbon-hydrogen bonds with oxygen to form carbon dioxide and water, at the end of the reaction, virtually every molecule of gasoline, the H18 molecule, has disappeared. But in nature, we need to gain exquisite control over chemical reactions, and that engages the issue of equilibrium chemistry. And by equilibrium chemistry, it implies immediately that we've got a balance between reactants and products. But more than that, we've discussed free energy, which is the primary determination of spontaneity in a chemical reaction. So we want to relate this question of equilibria in chemical reactions to the free energy. And that places the entire discussion of equilibrium chemistry on a free energy surface. And one of the most famous examples of this is the Haber process. And the Haber process takes N2 in the gas phase, and as we know, N2 has an extremely strong triple bond, and it reacts N2 with hydrogen gas to form the ammonia molecule also in the gas phase. And we have to balance this reaction. We have to have 2 ammonia on the right side reacting with 3 hydrogen and 1 nitrogen on the left-hand side. But the remarkable thing is, if we start with pure nitrogen and hydrogen in this reaction, and typically this reaction is run at 700 Kelvin and about 20 atmospheres pressure, that reaction proceeds toward the formation of ammonia, and it proceeds because it's moving down a free energy surface, so delta G is less than 0, which means that that reaction is spontaneous. And it moves forward, forming more and more ammonia until it reaches a critically important point, and that's the point of chemical equilibrium. And as we know, that's the point where delta G, the change in free energy, is 0. And as soon as the change in free energy is 0, there is no chemical motivation for changing the balance between the amount of reactants and the amount of products. Now, that isn't to say that the reactions aren't proceeding. In fact, the reactions proceed very quickly, combining nitrogen and hydrogen to form ammonia. But at the same time, ammonia is breaking up to reform nitrogen and hydrogen at the same rate. So while the reaction is dynamic, it's static with respect to the relative concentrations of the species, the reactants and the products. But remarkably, we could also start this reaction with pure ammonia. And in that case, again, delta G is less than 0, and we move spontaneously down the free energy surface until we reach the same equilibrium position. And you can see in a reaction like this, if we control the balance between reactants and products, we have exquisite control over the system because we have both reactants and products available to us. And so this forms a critically important class of chemical reactions characterized by this delicate balance between the conversion of reactants to products and the conversion of products back to reactants. And so we couple then in the continuing discussion the idea of a chemical equilibrium with the idea of the change in Gibbs free energy. So let's look at this example of chemical equilibrium. There are many different examples of this. Now, this production of ammonia turns out to be extremely crucial because ammonia breaks the N2 bond and makes the available nitrogen susceptible to use by plants, and so therefore ammonia is the dominant fertilizer, and that's revolutionized our ability worldwide to produce food which can then support people. And a major fraction of the Earth's population increase in humans has come strictly from the ability to form ammonia to fertilize crops to increase food production. But there's another major type of reaction that is an equilibrium reaction, and that's an acid-base reaction. In this case, we are placing acetic acid into water. And when we do that, the acetic acid molecule reacts with the water molecule, and it reacts with the water molecule by moving a hydrogen from the acid to water to form H3O+, the hydronium cation, leaving the acetate anion as another product. But interestingly, the equilibrium is such that the forward reaction matches the rate of the back reaction under conditions of very small fraction of the acetic acid dissociating in water. Another important use of equilibrium chemistry is in the creation of biofuels. And biofuels primarily occur from two different sources. There are second-generation biofuels that use switchgrass and poplar to form liquid fuels, and those liquid fuels are used and will be increasingly used by aircraft, because when we looked at the thermodynamics of heat pumps and electric cars, it turns out that the entire infrastructure of society can be run off of electricity from renewables, with one important exception, and that's the fuel required to supply the energy to aircraft. But as we will see, our ability to produce biofuels is perfectly adequate to supply all of the jet fuel required to sustain all types of aircraft flights. Now there's another type of biofuel, and that's ethanol. And as we'll see in our study of the equilibrium reactions for the production of ethanol, you have to be very careful about how you produce that ethanol, because much of the corn-based ethanol that's used now actually requires more energy, more carbon output that is destructive to the climate than is saved by the use of ethanol. So we'll see that equilibrium chemistry can decide between a wise formation of biofuels and an unwise one.